Welcome back to Basic Electronics. In the last class, we have presented two approximations which can be used in op-amp circuit analysis when the op-amp is operating in the linear region. In this class, we will look at two op-amp based amplifier configurations, the inverting and non-inverting amplifiers. We will see that the analysis as well as design of these circuits is very easy, almost trivial. So let us get started. Let us start with this circuit here. The non-inverting input of the op-amp is connected to ground. That is the input voltage. That is the output voltage. And we will work out the relationship between the input and output. The load resistance is connected here, and we have shown that with dashed lines because we will see that whether we connect RL or not, the functionality of the circuit does not change. To begin with, we note that V plus and V minus are nearly the same, and therefore V minus is 0 volts because V plus is 0, and that tells us that I1, this current, is Vi minus 0 divided by R1, that is Vi by R1. Now let us note that the non-inverting input here is at real ground. It's physically connected to ground, and the inverting input is at virtual ground. So this node is also at approximately 0 volts, but it is not physically connected to the ground node. Let us now use the second golden rule. This was the first one, and that is that the input current of the op-amp is 0. So in this circuit, this current marked I is 0, and therefore I1 goes through R2. So this current must go around like that because no current can enter the op-amp. And that tells us that VO, this voltage, is V minus this voltage drop. What is that voltage drop? That is I1 times R2. So VO is V minus I1 times R2. V minus, as we saw earlier, is nearly equal to V plus, which is 0, and I1 is Vi by R1. So that tells us that VO is 0 minus I1, which is Vi by R1 times R2, and that turns out to be minus R2 divided by R1 times Vi. So VO is proportional to Vi, and if R2 by R1 is larger than 1, then we have an amplifier. And the relationship between Vi and VO has a negative sign. That means they are out of phase. And now we understand why this circuit is called an inverting amplifier. Inverting because we have this minus sign here. Amplifier because we can choose R2 and R1 appropriately so that R2 by R1 is greater than 1. So therefore the output voltage is an amplified version of the input voltage. Alright. Now the next question that we must address is, where does this current go? The current that we have shown over here. And here is the answer to that question. Let's take an example. Say Vi is 0.1 volt, R2 is 10K, R1 is 1K. So the gain is minus 10K by 1K, that is minus 10. If Vi is 0.1 volt, then VO would be 10 times that, minus 10 times that, that is minus 1 volt. Now in this scenario, we have 0 volts here, minus 1 volt here. So therefore, the current through RL would be like that. We have 0.1 volt here. The inverting terminal is at virtual ground. So we have a current going like that. And these two currents essentially combine and enter the op-amp as shown here. And in this situation, we say that the op amp is sinking this current. And if the current was in the other direction, then we would say that the op amp is sourcing that much current. Now the 741 op amp can source or sink about 25 milliamps, not more than that. And in the circuits that we come across in this course, we will not really exceed this limit, but nevertheless, it is important to keep this number in mind. If you have to design a new op amp circuit, then you should check whether the current that the op amp has to sink or source is within this limit or not. Alright. Now what we will do is go inside the op amp, that is, look at the internal circuit of the 741 op amp and see what exactly is happening when we say that the op amp is sinking a current or sourcing a current. And here is the internal circuit of the op amp again. And when we say that the op amp is sinking a current, that means a current is entering like that. What is actually happening is the current enters like that and goes through this Q20, the transistor, and eventually to this minus VEE power supply. And that is how the circuit is completed. When we say the op amp is sourcing a current, that means a current is coming out of the op amp, then the path that the current takes is from VCC through Q14 and out like that. So these currents are actually getting supplied by the power supply, and that becomes clear when we look at this internal circuit of the op amp. Here is a sample simulation result for the inverting amplifier. We have R2 equal to 10K, R1 equal to 1K. So the gain of this amplifier is minus 10K divided by 1K, or minus 10. So we expect VO to be 10 times VI with a negative sign. The input is a sinusoid with an amplitude of 0.5 volts and frequency 1 kilohertz. And we have shown the load resistor here, but as we have seen in the last slide, it really does not change the relationship between VO and VI. So we have not put down a value for this RL. Here is the input voltage. The amplitude is 0.5. This is 1 volt here, 0.5, and the frequency is 1 kilohertz. So the period from there to there is 1 millisecond. The output voltage is expected to be 10 times larger in amplitude. So that is 0.5 times 10, or 5, and that is what we see, 5 volts in amplitude. And of course it's out of phase with respect to the input voltage because of the negative sign in the inverting amplifier relationship. So the output voltage therefore goes negative when the input voltage goes positive. Let us make a few observations. The gain of the inverting amplifier is minus R2 by R1, as we have already seen, and it is called the closed loop gain to distinguish it from the open loop gain of the op amp, which is very large, 10 raised to 5 or so for the 741 op amp. Now this open loop refers to a configuration in which there is no connection between the output side and the input side, like this one, and the op amp is then said to be operating in the open loop configuration. In contrast, this configuration is called closed loop configuration. The gain can be adjusted simply by changing R1 or R2, and that follows from this expression. You want a gain of 10, make this 10K, make this 1K. You want a gain of 20, make this 20K, make this 1K. It's as simple as that. And let us compare that simplicity with another amplifier we have seen earlier, that is the common emitter amplifier. For the common emitter amplifier, on the other hand, the gain was minus Gm times Rc parallel RL. So first of all, it depended on the load resistance. This one does not. And also it depends on Gm. So the gain depends on how the BJT is biased, because Gm has a dependence on IC. So it surely is not as simple as using an op-amp circuit for amplification. There is a ready-made circuit file which you can check out and generate these results and change this resistance value and so on. So we have seen that an inverting amplifier provides a gain of minus R2 by R1. However, there are some limitations that we need to understand. Number one, this output voltage is limited to plus minus Vsat, where Vsat is the saturation voltage of the op-amp. So point number one, the output voltage is limited to plus minus Vsat. What is Vsat? Vsat is about 1.5 less than the supply voltage VCC. So if VCC is 15 volts, for example, then Vsat would be 13.5 volts. That means the output voltage would be limited to 13.5 volts on the positive side and minus 13.5 volts on the negative side. Here is an example. The input amplitude is 2 volts. The amplifier gain is minus 10, and therefore we expect an output voltage amplitude equal to 10 times 2 or 20 volts. That means we expect the output voltage to go up to 20 volts in the positive direction and minus 20 volts in the negative direction. But because of saturation, the output voltage is limited here by Vsat and here by minus Vsat. And this is something that you can easily check in the lab. So hook up this circuit in your electronics lab and observe the waveforms. As you keep increasing the input amplitude, at some point you will start seeing this effect of saturation. There is another limitation that arises for a practical op-amp, and that has to do with the signal frequency. If the signal frequency is too high, the input signal frequency, a practical op-amp cannot keep up with the input due to its slew rate limitations. And let us see what this slew rate is. The slew rate of an op-amp is the maximum rate at which the op-amp output can rise or fall. And for the 741 op-amp, the slew rate is 0.5 volts per microseconds. So in 1 microsecond, the op-amp output can only rise or fall by 0.5 volts. Here is an example. It is the same circuit that we saw earlier. R2 is 10K, R1 is 1K, so the gain is minus 10K by 1K or minus 10. Vm is 1 volt. And the frequency now is higher, it's 25 kilohertz. 25 kilohertz corresponds to a period of 40 microseconds. So that is one period. This is the input signal going from minus 1 volt to plus 1 volt. And the output that we expect is 10 times the input voltage, so an amplitude of 10 volts, and of course it's going to be out of phase with the input voltage. So that is the output voltage that we expect. But the actual output that we observe, and you will observe this also on an oscilloscope if you connect this circuit in the lab and make measurements. The actual output that we observe is this here. It looks substantially different from what we expect. And this is entirely because of the slew rate limitation of the 741 op amp. Let us calculate this rate here. What is this voltage difference? Each division here is 2 volts, so it is 2, 4, 6, 8, about 10 volts from there to there, and this time is 20 microseconds. So it is 10 volts, delta V is 10 volts and delta T is 20 microseconds. So 10 volts divided by 20 microseconds, that comes to half volt per microsecond, and that is exactly what the slew rate of the 741 is. And this happens because this rate at which the output is expected to rise is higher than the slew rate, and so therefore the op amp cannot really keep up with that. So this is definitely a limitation in practice, and we should be aware of that. So what it means is we cannot use the inverting amplifier at arbitrarily high frequencies. If our input frequency is higher and there is an op amp available with higher slew rate, then that may be a solution. Otherwise, we have to look for some other circuit. Let us now address a very important question, and that is, what if the non-inverting and inverting inputs of the op amp are interchanged? This is our inverting amplifier. The non-inverting input here is going to ground. What will happen if we interchange this plus and minus to get this circuit? So this circuit is the same as the first circuit, except here the inverting input is going to ground. Now if we go back to our analysis of the inverting amplifier, we assume that the op amp is operating in the linear region. Then we said that this V minus and V plus are nearly equal, so this is also 0 volts. Then we calculated this current. Then we said that this current cannot go into the op amp, so it must go around like that, and then we arrived at VO. We can do the same thing for this circuit and once again get the same result, but there is a very serious problem when we do that. And the problem is the following. From circuit 1 to circuit 2, the nature of the feedback changes from negative to positive. And where is the feedback in these circuits? That is this connection from the output back to the input side through R2. In circuit 1, the feedback turns out to be negative, and we will see later how to identify whether the feedback is positive or negative. In this circuit, it is negative, and when the feedback is negative, circuits are stable, and our assumption that the op amp is working in the linear region holds in this case. And then we can do our analysis like we have seen earlier and arrive at this result. In circuit 2, the feedback turns out to be positive, and with positive feedback circuits become unstable, and therefore this assumption that the op amp is working in the linear region does not hold for circuit 2, and therefore all of this derivation goes for a toss. This relationship does not apply anymore, and therefore circuit 2 is not an amplifier. It turns out that circuit 2 is also useful for some other purpose, and we will discuss that later. Here is another very commonly used circuit in which the op amp operates in the linear region. The input is connected to the non-inverting op amp input, that is the output, and let us see how this works. Since the op amp is assumed to be in the linear region, V plus and V minus are nearly equal, and therefore V minus is nearly equal to Vi. And once we know this voltage, we can find this current, that is 0 minus V minus, which is the same as Vi, divided by R1. So minus Vi divided by R1, that is I1. Now since the op amp input current II here is 0, I1 and I2 must be the same, and now we have a way to calculate VO. So what is VO? VO is this voltage V minus minus this voltage drop. So VO is V minus minus I2 R2, that voltage drop. V minus is the same as V plus, I2 is the same as I1, so that is V plus minus I1 times R2. V plus is Vi, I1 is minus Vi divided by R1, and when we put it all together we get Vi times 1 plus R2 over R1. So for this circuit we have the output voltage equal to the input voltage times 1 plus R2 over R1. So this circuit is also an amplifier, and it is known as the non-inverting amplifier because this gain is a positive number now, unlike the previous amplifier, which was the inverting amplifier with a negative gain. Once again, given the value of gain, it is very easy to choose R2 and R1. For example, if we want a gain of 10, we can choose R1 equal to 1K, R2 equal to 9K, and get a gain of 1 plus 9 equal to 10. Once again, interchanging plus and minus, the non-inverting and inverting inputs of the op amp, changes the nature of the feedback from negative to positive, and the circuit operation becomes completely different. So this order is rather important in all op amp circuits, and we should always keep that in mind. One important question that now arises is which one of these is better, inverting amplifier or non-inverting amplifier? Of course, the inverting amplifier has a negative gain, whereas this one has a positive gain. That is negative, that is positive. But apart from that, they are both easy to use. We can easily find R1 and R2 for a given value of gain. And suppose the sign of the output voltage is not a concern. So let's say we don't really mind this negative sign there. Then which configuration should be preferred? So that is the question that we want to answer now. Let us now replace the op amp with its equivalent circuit like that. We have the input resistance of the op amp appearing between the non-inverting and inverting input terminals. Then we have the voltage control voltage source, which represents the gain of the op amp, and then we have the output resistance of the op amp. Our interest is to find the input resistance as seen by this voltage source Vs. And what is that? That is Vs divided by I1. Now since V minus is nearly 0, V minus and V plus are nearly the same, and therefore V minus is 0. I1 is Vs minus 0 divided by R1, or simply Vs divided by R1. So I1 is Vs by R1, and therefore Rin, which is Vs divided by I1, is R1. And R1 would typically be in the kilo ohms range. Let us now look at the non-inverting amplifier. Once again, let us replace the op amp with its equivalent circuit. and that is what we have: the input resistance, then the gain element, then the output resistance. In this case, the input voltage is applied at the non-inverting input of the op amp, right there. And now we can see that this voltage source will see a large resistance, because this Ri is very large, typically something like mega ohms. In fact, it turns out to be much larger than simply Ri. It is Ri times AV times some factor, and we will actually derive this result later. So this is really quite huge, and therefore for all practical purposes Vs is looking at an open circuit. So this is really a big advantage of the non-inverting configuration. If we are concerned about the resistance seen by the input voltage source, then we should definitely choose the non-inverting amplifier configuration. Let us have a revision of what we have studied. Here are the inverting amplifier and non-inverting amplifier side by side. As we see, there are some similarities between these two circuits. Both of these have two resistors, R1 and R2. And in both cases, the feedback resistor goes from the output to the inverting input of the op amp, there as well. And there are also some differences, of course. And the inverting amplifier, of course, has this negative sign in the gain. Apart from that, note that we have only one term in this expression. Here we have two. And let us see where this term came about. V minus in this case was 0, and the output voltage was 0 minus this drop. And what we see here is essentially just this drop, because V minus was 0. On the other hand, for the non-inverting amplifier, PO has two terms, and these two terms came about because Vi is nearly Vs, and then there is this voltage drop. So VO is V minus this voltage drop, and that V minus was equal to Vi or Vs as it is called here. And that is why we have two terms here. And as we have also seen, there is a large difference between the input resistances of these two circuits. In this circuit, the input resistance is R1, as seen by the voltage source, the input voltage source. And in this circuit, in the non-inverting amplifier, the input voltage source sees a much larger resistance. So it's a good idea to stop the video at this point, draw these circuits yourself, turn the monitor off, derive the VO versus VI relationships for both of these circuits. And it's best not to learn these by heart. It's very easy to derive these relationships, as we have already seen, and when you go through the derivation, it will stay with you much longer than just learning things by heart. In summary, we have looked at two op-amp based amplifier configurations. The gain is negative for the inverting amplifier and positive for the non-inverting amplifier. In either case, the gain can be adjusted simply by choosing two resistance values. We have also seen that the non-inverting amplifier is better because it offers a higher input resistance. In the next class, we will continue this discussion. Until then, goodbye.